For nearly a century, one idea has quietly shaped everything we think we know about the cosmos. The universe is expanding, not as a metaphor or a philosophical concept, but as a measurable, physical reality where space itself stretches in every direction, carrying galaxies apart across unimaginable distances. And yet, there is a deeper question hidden beneath that certainty, one that is rarely asked out loud, because it sounds almost unreasonable at first. But what if the expansion of the universe is not what we think it is? What if the very thing we use to explain the origin, evolution, and fate of everything is only an approximation of something far stranger? Because if expansion is misunderstood, then distance may not mean what we think it means. Time may not flow the way we assume, and the story we tell about the beginning of the cosmos under the Big Bang theory may only be a surface level interpretation of a deeper process that we have not yet learned how to see. And this is not just an abstract problem for physicists, because the expansion rate defines the age of the universe, determines how structures form, and shapes every model we use to describe reality at the larger scales. Meaning that if our interpretation is even slightly off, the consequences ripple through everything from galaxy formation to the nature of dark energy. And yet, despite how foundational this idea is, there is a growing unease within cosmology. Not a dramatic collapse or a sudden contradiction, but a persistent mismatch between different ways of measuring the same phenomenon, where independent observations refuse to align cleanly, as if the universe is giving us answers that depend on how we choose to look at it. And that raises a subtle but profound possibility that we are not simply refining a well-understood model, but instead pressing against the limits of a framework that may no longer be complete. Because we assume that expansion is a single, consistent process unfolding uniformly across time and space. But what if it is not? What if what we call expansion is not one thing but several overlapping effects? Or worse, what if it is not expansion at all in the way we imagine it? And if that sounds unlikely, it is worth remembering that scientific models have been overturned before. Not because they failed completely, but because they worked almost perfectly until measurements became precise enough to expose their hidden assumptions. And now, as our instruments become more sensitive and our observations more exact, we may be approaching a similar threshold, where the question is no longer how fast the universe is expanding, but whether we ever truly understood what expansion meant in the first place. To move beyond that question, we need to understand the system we are working within. Because modern cosmology does not treat the universe as a static backdrop, but as a dynamic structure governed by the equations of general relativity, where space and time are woven together into space-time, capable of stretching, bending, and evolving under the influence of mass and energy. And within this framework, expansion is not something happening inside the universe. It is something happening to the universe itself. Meaning that when we observe distant galaxies drifting away, we are not seeing motion through space in the usual sense, but rather the gradual increase of the space between them, like points drawn on the surface of an inflating sphere. A model that has proven remarkably effective at describing large-scale observations, from galaxy distributions to the relic radiation left over from the early cosmos. And at the center of this entire description lies a single parameter that holds the model together: the Hubble constant, which quantifies how fast the universe expands at the present moment, linking distance to velocity in a way that allows astronomers to reconstruct the past and predict the future. Because if you know how quickly galaxies are separating today, you can rewind that motion backward to estimate when everything was once compressed into a much denser state, and forward to understand how the cosmos will continue to evolve, whether it will expand forever, slow down, or tear itself apart under the influence of dark energy. But measuring this number is not as simple as it might seem, because the universe does not come with a built-in ruler. So scientists rely on indirect methods that build upon one another. The most direct approach, using nearby astronomical objects whose intrinsic brightness is known, such as Cepheid variable stars and Type 1a supernovae, which act as cosmic markers, allowing distances to be estimated step by step in what is known as the tablet-fork distance ladder, each rung extending our reach further into space. While a completely different approach looks not outward but backward in time, analyzing the faint afterglow of the early universe known as the cosmic microwave background. A snapshot of the cosmos when it was only a few 100,000 years old, long before stars and galaxies existed. And by interpreting subtle fluctuations in this radiation, scientists can infer what the expansion rate must be today, provided the underlying cosmological model is correct. And in theory, these two methods should agree, because they are describing the same universe from two different perspectives, one local and one primordial. But this agreement depends on several critical conditions being satisfied. The physics governing light and matter must remain consistent across billions of years. The calibration of distance indicators must be accurate and free of systematic bias. And the model connecting early universe conditions to the present must correctly account for all relevant components, including dark matter and dark energy. Any deviation in these assumptions can shift the inferred expansion rate. And yet, despite decades of refinement, increasing precision, and independent verification, the results continue to diverge in a statistically significant way, suggesting that either subtle errors persist in one or both methods, or that something more fundamental is missing from the model itself. And this is where the stability of the entire framework begins to show its limits. Because the standard cosmological model, while extraordinarily successful in explaining a wide range of observations, is built on parameters and components that are not directly observed, such as dark energy, which is invoked to explain the accelerating expansion, and dark matter, which shapes the formation of large-scale structure. And if even one piece of this interconnected system is slightly mischaracterized, the consequences propagate through every calculation. Meaning that the disagreement in the expansion rate is not just a technical issue, but a signal that the rules we are using to describe the universe may be incomplete. Not obviously broken, but subtly misaligned, in a way that only becomes visible when measurements become precise enough to expose the gap between what we expect to see and what the universe actually reveals. If that gap is real, then the first instinct is to look for errors in the most direct method, the local measurements, because they rely on layered calibrations where small uncertainties can compound. So case 1 begins with the assumption that the cosmic distance ladder is flawed, that perhaps objects like Cepheid variable stars are not as reliable as we believe, or that dust, metallicity, or environmental effects subtly distort their brightness, leading to incorrect distance estimates. And for a time, this seemed plausible, because even a small systematic bias could shift the inferred value of the Hubble constant enough to resolve the discrepancy. But as instruments improved, and independent teams recalibrated these measurements using different techniques, including geometric distance indicators and alternative standard candles, the results remained consistent, tightening rather than closing the gap, suggesting that the problem does not originate simply from observational error in the local universe. Which leads naturally to case 2, the idea that the issue lies not in nearby measurements, but in our interpretation of the early universe. Specifically, the data derived from the cosmic microwave background. Because this method does not measure expansion directly, it infers it through a model that assumes certain conditions about the composition and evolution of the cosmos. So perhaps those assumptions are incomplete. Perhaps dark energy behaves differently over time, or additional relativistic particles existed in the early universe, altering the expansion history in subtle ways. And for a moment, this opens a new possibility that the tension is not an error but a clue pointing toward new physics beyond the standard model. Yet, as more precise observations from missions like Planck and other surveys are analyzed, the inferred values remain remarkably stable within that framework, resistant to simple modifications, meaning that adjusting early universe physics without divide by the breaking other successful predictions proves far more difficult than expected. Which brings us to case 3, a more complex scenario where the universe is not as uniform as assumed on the largest scales. That perhaps we happen to reside in a region of space with slightly different density or expansion properties, a large-scale cosmic void that makes local measurements appear faster compared to the global average. And this idea is intriguing because it does not require rewriting fundamental physics, only relaxing the assumption of perfect homogeneity. But when tested against large-scale surveys of galaxy distributions and cosmic structure, the evidence for such a significant local deviation remains weak. And even if such a void exists, it would need to be improbably large and finely tuned to fully account for the observed discrepancy, which makes it an unlikely solution rather than a convincing one. And so we arrive at case 4, the most subtle and perhaps the most unsettling possibility, that neither set of measurements is fundamentally wrong, but that they are each correct within different regimes of a universe whose behavior changes over time in ways our current models do not capture. That the expansion rate is not a single fixed quantity but evolves with hidden dynamics, perhaps influenced by interactions between dark energy and matter or by modifications to gravity itself on cosmological scales. And this idea comes closest to reconciling the data without outright contradiction. But it carries a cost, because it implies that the elegant simplicity of the standard cosmological model may be an approximation, not a complete description. And as each of these cases is examined in turn, tested, refined, and often partially ruled out, a pattern begins to emerge, not of failure in any single method, but of tension distributed across the entire framework, where every solution introduces new complications elsewhere, and every attempt to resolve the discrepancy exposes deeper assumptions that had previously gone unquestioned, leaving us in a position where the evidence does not point cleanly in one direction, but instead suggests that the problem may not lie in the measurements alone, but in the way we have chosen to interpret what those measurements mean in the first place. And if the problem is not confined to any single method, then we are forced to confront something that has been quietly present from the beginning but rarely questioned directly. An assumption so deeply embedded in modern cosmology that it often goes unnoticed. The idea that the universe is homogeneous and isotropic on the largest scales, formalized as the cosmological principle, which states that no matter where you are in the universe, and no matter which direction you look, the large-scale properties should be essentially the same. And this principle is not just a philosophical preference. It is the foundation upon which the entire interpretation of expansion is built. Because without it, the equations derived from general relativity no longer simplify into the clean, predictable models we rely on. And the meaning of the Hubble constant itself becomes far less straightforward. Because it assumes that the rate of expansion is a global property, not something that depends on location or direction. But what if this assumption, while approximately true, is not exact? What if the universe is only statistically uniform, with subtle but significant variations that become visible only at the level of precision we have now reached? Because when we examine large-scale structures, we do not see a perfectly smooth distribution of matter. We see filaments, clusters, and vast voids stretching across hundreds of millions of light years, forming what is often called the cosmic web, a structure that is far from uniform on intermediate scales. And although the standard model assumes that these irregularities average out at the larger scales, that assumption has never been tested with absolute certainty, especially given the limits of our observable horizon. And this is where the hidden implication begins to emerge. Because if the universe is not perfectly homogeneous, then the light we observe from distant objects may be passing through regions of space with different expansion, histories, gravitational influences, and energy distributions. Meaning that what we interpret as a single uniform expansion rate could in fact be an emergent average of many local behaviors, each slightly different from the others. And if that is the case, then the discrepancy we call the Hubble tension is not a flaw to be corrected, but a signal that we are compressing a more complex reality into an oversimplified parameter. And this changes the question entirely. Because instead of asking which measurement is correct, we must ask whether it even makes sense to expect a single value at all. And as we push this idea further, the implications become increasingly difficult to ignore. Because a non-uniform expansion would affect not just distance measurements, but the inferred age of the universe, the interpretation of the cosmic microwave background, and the role of dark energy itself, which is currently treated as a uniform field driving acceleration, but may instead reflect the collective behavior of a universe whose geometry and energy distribution vary more than we assume. And in this light, the tension between early and late measurements is no longer a contradiction, but a boundary. A place where our current model begins to lose resolution, revealing that the simplicity we observe may be a projection of limited perspective rather than a fundamental property of reality. And from here, a new possibility begins to take shape, one that is both unsettling and intellectually compelling. That the expansion of the universe is not a single coherent process unfolding identically everywhere, but a phenomenon that depends on scale, structure, and perhaps even the path that light takes through space-time. Suggesting that what we call expansion may not be a universal rule, but an emergent pattern arising from deeper, more complex dynamics that we have only just begun to glimpse. If that emerging picture is even partially correct, then for a brief moment, it seems as though the tension finally makes sense, not as a failure, but as a reflection of a richer structure, a universe where expansion is not a single global number, but an effective description that depends on where and how it is measured. A perspective that appears to reconcile the mismatch without discarding the success of general relativity. And in this view, the discrepancy between local observations and early universe inference is no longer a contradiction, but an expected outcome of averaging over a complex cosmic web, suggesting that the so-called Hubble tension might dissolve once we replace a single parameter like the Hubble constant with a more nuanced description of expansion that varies with scale and structure. And for a moment, this feels like resolution, a way to preserve the foundations while extending the model just enough to accommodate the data. But this is where the problem deepens. Because the moment we allow expansion to vary in this way, we begin to undermine the very assumptions that made cosmology predictive in the first place. Since the interpretation of the cosmic microwave background relies critically on the idea that the universe can be described by a small set of global parameters. And if those parameters lose their universality, then the connection between early conditions and present observations becomes ambiguous, meaning that the same data could correspond to multiple underlying realities. And this is not just a technical inconvenience. It is a conceptual shift that transforms cosmology from a model-driven science into something closer to an inverse problem with no unique solution. And the implications extend further, because if expansion is not uniform, then the inferred age of the universe may not be a single value either, but a range that depends on the path taken through space-time, raising the possibility that different regions could have effectively different cosmic histories. A notion that begins to blur the boundary between cosmology and relativity in a way that is difficult to reconcile with a coherent global timeline. And yet, the deeper paradox emerges when we consider that the very structures we are invoking to explain the discrepancy, the inhomogeneities, the voids, the clustering of matter, are themselves predicted by the standard model that assumes uniform expansion on large scales, meaning that the solution depends on the same framework it seeks to modify. And this creates a loop that is hard to escape, because if we adjust the model to account for variable expansion, we risk invalidating the conditions under which those structures formed. And if we preserve the model to maintain consistency, we are left with a discrepancy that refuses to disappear. And in this sense, the proposed solution begins to resemble the original problem, not a resolution, but a redistribution of uncertainty. And it becomes increasingly unclear whether we are uncovering a deeper layer of reality or simply stretching the existing framework beyond its natural limits. And this tension sharpens further when we consider alternative explanations that attempt to modify gravity itself, introducing extensions to general relativity on cosmological scales, which in principle could alter the relationship between distance and expansion without invoking new forms of energy. But these modifications often succeed in resolving one aspect of the data only to conflict with others, such as galaxy dynamics or gravitational lensing, suggesting that the problem is not isolated but woven into multiple independent lines of evidence. And so we arrive at a point where each path forward carries a cost. Preserving the simplicity of a uniform expansion leaves us with a persistent and unexplained tension, while embracing a more complex, scale-dependent picture dissolves the predictive clarity that made the model so powerful. And perhaps the most unsettling possibility is that both perspectives are incomplete. That what we interpret as expansion, whether uniform or variable, is not the fundamental process at all, but an emergent effect arising from deeper principles that we do not yet understand. And if that is the case, then the frameworks we are trying to reconcile may be approximations of something that cannot be fully captured within their current assumptions, leaving us with a contradiction that cannot be resolved simply by refining measurements or adjusting parameters, but only by rethinking what it means for the universe to expand in the first place. And so we are left not with a broken theory, but with a theory that works almost too well within its own assumptions. A framework that continues to predict and describe an enormous range of observations while quietly failing to reconcile one of its most fundamental parameters. And this is what makes the situation so difficult to interpret. Because nothing has collapsed, no single equation has failed, and yet the mismatch remains. Persistent across methods, instruments, and refinements, suggesting that the issue is not located in any one place but distributed across the entire structure of the model. And in that sense, the tension is not an anomaly to be removed, but a boundary we have reached. A point where the language we use to describe the universe begins to lose precision, where a concept like the Hubble constant, once treated as a definitive quantity, starts to look more like an approximation of something that cannot be fully captured by a single number. And if that is true, then the question is no longer which value is correct, but whether the idea of a single value was ever appropriate to begin with. And this reframing shifts the focus away from resolving a discrepancy toward understanding what kind of reality could produce it. Because a universe in which expansion depends on scale, structure, or observational pathway is not just more complex, it is fundamentally different from the one we thought we inhabited. And the implications extend beyond cosmology into the nature of measurement itself. Since every observation we make is filtered through light that has traveled across vast and uneven regions of space-time, meaning that what we interpret as a global property may always be an integrated signal shaped by the journey it has taken. And in that sense, the act of observing the universe is inseparable from the structure of the universe. A feedback loop where the data we collect is already conditioned by the assumptions we use to interpret it. And this begins to blur the line between objective description and model-dependent inference, raising the possibility that some aspects of cosmic reality may not be directly accessible as single consistent quantities, but only as overlapping perspectives that resist full unification. And if that sounds abstract, it becomes more tangible when we consider that even the earliest light we observe, the cosmic microwave background, is not a direct snapshot, but a reconstructed signal interpreted through a model that assumes uniformity and coherence across scales we cannot fully verify. And so, the deeper implication is not that our measurements are wrong, but that the framework connecting them may be incomplete in a way that cannot be resolved by incremental adjustments. Because it is tied to assumptions about symmetry, uniformity, and the nature of space-time itself. And from here, the question begins to expand beyond expansion. Because if the largest structure we can observe resists a single consistent description, then what does that imply about other foundational concepts we take for granted? About time as a global parameter, about causality across cosmological distances, about whether the universe can be described by a single coherent history at all. And it is here that the problem becomes less about numbers and more about interpretation, less about measuring the universe and more about understanding what kind of system we are embedded within. Because a reality in which fundamental properties depend on perspective is one that challenges the idea of a complete, observer-independent description. And yet, we are still at the earliest stage of confronting this possibility, with data that is precise but not yet decisive, with models that are powerful but not yet complete, and with a tension that refuses to resolve into either confirmation or refutation, leaving open a space where multiple interpretations remain viable. And perhaps that is where the most important insight lies, not in choosing between them too quickly, but in recognizing that the question itself may need to change. Because if expansion is not a single process unfolding uniformly across the cosmos, then the story we have been telling about the universe, from its origin to its fate, may be a simplified narrative imposed on a far more intricate reality, one in which the patterns we observe are real but not fundamental, coherent but not complete. And if that is the case, then the next step is not simply to measure more precisely, but to reconsider what it is we are trying to measure in the first place, and whether the concepts we rely on are sufficient to describe a system that may not conform to the kind of unity we expect. Because if the universe does not present itself as a single, consistent expansion, but as something that depends on scale, structure, and observation, then the question is no longer just how it evolves, but whether it can be fully described from any single point of view. And so the tension remains, not as a flaw that can be easily corrected, but as a signal that something in our understanding has reached its limit. Because every path we have followed leads to the same place. A model that continues to explain almost everything while quietly failing to unify one of its most fundamental measurements. And this forces an uncomfortable recognition that the expansion of the universe, as described through the Hubble constant, may not be a single, well-defined property, but an approximation shaped by the assumptions we bring into the act of measurement. And if that is the case, then resolving the discrepancy is no longer about choosing which number is correct, but about understanding why we expected a single number at all. Because the deeper issue may not lie in the data, but in the structure of the questions we are asking. And once that possibility is taken seriously, the implications begin to extend beyond cosmology itself. Since the idea that large-scale properties depend on perspective challenges the notion that reality can always be reduced to a unified, observer-independent description, suggesting instead that what we perceive as consistent may emerge from averaging over complexity rather than reflecting something fundamentally simple. And this has echoes in other areas of science, where systems that appear stable at one scale reveal hidden variability at another, raising the possibility that the universe itself operates in a similar way, presenting coherence at the level we can observe while concealing deeper layers that do not conform to the same rules. And if that is true, then the expansion we measure may be less like a universal law and more like a pattern, something real and meaningful, but not ultimately fundamental. And that shifts the focus from asking how fast the universe is expanding to asking what kind of process could give rise to the appearance of expansion in the first place. Because if different methods yield different answers, and if those answers cannot be reconciled within a single framework, then perhaps they are not meant to be reconciled in the way we expect, and instead reflect multiple aspects of a reality that cannot be fully captured from a single perspective. And if that sounds like a limitation of our knowledge, it may also be a clue pointing toward a deeper structure in which concepts like space, time, and expansion are not fixed ingredients, but emergent features of something more fundamental, something that does not present itself directly, but only through the patterns we are able to detect. And if that is the case, then the tension we observe is not a problem to be solved, but a boundary to be crossed. A place where the familiar begins to give way to something less intuitive, less certain, and perhaps more revealing. Because if the universe does not expand in the way we think it does, then the question is no longer how it grows or how it will end, but whether the story we have been telling about its evolution was ever the right story to begin with.